Hey, hello everyone. Hope you're doing all right. So let's take a look at the syllabus, just so we're all on the same page about what's happening this week. So the snow days didn't really affect us, so we're just going to stay on schedule. We still didn't formally have a lab this week, so you don't have a lab due yet. You do have chapter 2 of Mastering Chemistry that'll be due on Sunday, so make sure to get that in. And then next week will be when we run our first quote unquote lab experiment. Now, we aren't going to meet formally in lab. So just to reiterate where you do this lab. So let's say, because of scheduling, you've already got Monday scheduled out, like where you won't have your kids or whatever, and that's when you want to get your lab done. So you're going to go ahead and open up Moodle. You need to have a physical copy of the lab manual, so you need to get that from the bookstore, and you have a little bit extra time to do it. I don't know why I'm here. Okay, there we go. Oh, everything but what I want is opening. There we go. All right, so you will have a physical copy of your lab manual. You'll click on this link here, which is going to be your data information. It's going to act as the experiment for you. It has all the labs for the whole semester, so if you want to work ahead, you can. You'll submit the experiment here. So the way you do that is take a picture or scan the document in and then submit it via Moodle. So, if you want, I would try and start getting that worked out. I guess won't be due on Sundays, right? We decided it would be due on Mondays so that you could have the lab portion to work on it. So for this first one, you may want to try and get it done before the final due date, just in case you're having any issues submitting stuff. I know sooner than later. All right, so let's keep working with chapter 2. The last time we met, we were talking about the difference between weight and mass. So they correlate to each other. So as mass goes up, your weight will go up. Mass is a measurement of how much material, how much matter is in an object. Weight, on the other hand, is dependent on gravity. So it's the effect of gravity on the given mass. So if you go out into space, your mass should stay consistent, but the weight will change. Hold on one second. Okay, so we had talked about the start of the metric system and different base units. So mass is going to be grams, length is going to be meters, volume is going to be liters, so on and so on. So when we want to make a unit bigger or smaller, we don't actually have to create a new unit. Like for instance, in the British system, we have inches. If I want to make a new unit or a larger unit, I have to convert it into yards, or I have to convert it into feet, or I have to convert it into miles, which are totally different unit structures. Here, I really can just add what's known as a prefix. So pre being in front. So these things just get stapled to the front of whatever your base is to make either a bigger or a smaller unit. On this chart here, right between the deca and the deci, this is the place that your base unit goes, okay? And I don't know why they don't put that in there, but that's the base unit. So let's say we're using the base unit of M, a meter. Well, if I want to make a unit that is 1,000 times bigger than my base unit, I would put kilo in front of it. It would be a km or a kilometer. If I wanted to make a unit, let's say that was 100 times smaller, because let's say the unit of a meter is too big. We're trying to measure, I don't know, the length of your fingernail. We don't want to use a meter. So we can use, let's say we do something that's 100 times smaller, or 100th, we could use a centi and call it a centimeter. Or we could use 1,000th and call it a millimeter. All of these, you'll notice, are increasing by a factor of 10, or we're adding a 0. As we move in this direction, we're decreasing by a factor of 10, right? The decimal is moving over one place. We can think of this base unit right here. So base as, if this is 10 and this is a 10th, it would be at the 1 value right in the middle. So we're moving the decimal over 1, then 2, then 3, so on and so on. Once on this chart, once you get past kilo and milli, the units start to increase by a factor of 1,000. So do you see how this is 1,000, and then the next one isn't 1,000 with an additional 0 for 10,000? It's a million. Okay, they add 3 zeros and then 3 zeros. This is the unit mega. We don't use this a whole lot in our class, but you may have heard like a megabyte back in the day before like our fancy cell phones now. We'd have megabytes. Now we're used to things like gigabytes, right? We count our information in gigabytes. If we have an external hard drive, we count them in terabytes. These units are sometimes used in chemistry. This class, again, I'm not really going to expect you to know outside of the kilo to milli. So know that micro, nano, pico, femto, those are small units, but I'm not going to test you on those. Like a picometer would be, the distance, a certain amount of distance between two like carbon atoms or something. So this is a super tiny amount. But you do need to know kilo to milli, okay? And I will show you a trick to learning those. So let's skip over for a second, and I want you to write this saying out. King Henry died, so King Henry died before drinking chocolate milk. It's silly, it's stupid, but you'll remember it. So just like when we read the sentence left to right, we want to think about this conceptually left to right. On the left side, this is the larger units. So large over here and small over here. The before, sometimes this, you'll see this written as King Henry died drinking chocolate milk, and they don't put the before in, but the before is important because that's our base unit, and we do have to hop through that as a decimal exchange. So before, if you want, you can put like a box around that, then that's our base unit. And again, some examples of a base unit could be meter, liter, gram, second, joule for energy. There's some other ones out there, but you really won't see anything outside of that. So king is kilo. Okay. Henry is hecto. We don't use that one a whole lot. So much so that I'm like, is it hecto or hecto? It's hecto, yeah. Died is deca, like a decagram or something like that, 10. Drinking is deci, a tenth. Chocolate is centi. Think century, 100, a cent, like a penny is 100th. And then milk is milli. Okay. So King Henry died before drinking chocolate milk. These are all of the prefixes that I expect you to be able to work with pretty quickly. When we write it in this order, it's nice because I can actually move or exchange my units really, really fast. So let's say I have 300 meters. That's my given information. And I want to find how many kilometers this is. Okay. Now, if this was in inches and this was in miles, we'd have to do all sorts of crazy stuff like divide by 12 and divide by 5,280. And I'll show you guys how to do that later. But this one's actually pretty easy. We just go, okay, what is the unit I'm starting with? I'm starting with a meter, and that's my base unit. So that's this thing right here. I want to go to kilometer, which is over at the king. So in order for me to go from the base unit to this larger unit, I need to take 1, 2, 3. Sorry, that last hop is not long enough. 1, 2, 3 hops with my decimal towards the left. So in 300 over here, I'm gonna just, let's move this over here. So 300. Where is my decimal? It's right there. So I need to do the same thing with my decimal that I did up here. So 1, 2, 3 hops over to the left. 1, 2, 3 hops over to the left. 0.3 kilometers. So fast, right? Can we do that with inches, feet, pounds, quarts? No, it's we don't get that. Let's try something in a different direction. So let's say that we have, given that we have 17.2 kilometers, and I want to find, for whatever reason, I want to find centimeters. So I'll use a different color for this one. So we're starting with the kilometer. That's the king, right? Or the kilo. I want to get to centimeter, which is over here, the centi. All right. So in order to get from king to centi, I need to hop 1, 2. You do go through the base. So 3, the base is a hop. 4, 5. I need to take my decimal and hop it 5 to the right. So let's write our number out here, 17.2. I need to move my decimal 5 hops to the right. 1, 2, 3, 4, 5. That's where the decimal is going to live now. In these empty spots here, I'm going to fill those in with zeros. Okay. So 17.2 kilometers, 17.2 kilometers is equivalent to 1,720,000 centimeters. So I want you to do one of these. Let's say that we're given, so we have, what do I want to do? 30, I don't know why I like 3 so much tonight. 30,500 milliliters. And I want to know, find how many liters that is. We do that conversion a lot. We go from liters to milliliters quite often. So look at your King Henry chart, figure out what unit you're starting with, what you're ending with, count your hops, and then move the decimal in the same direction. I'll give you guys about 30 seconds for that. All right, so I'll change the color up here. So we are going from a unit of a milliliter to a liter. In these first 2 problems, we used kilometers and meters. That's a unit of distance. Here we're using a unit of volume. It's okay, it follows the same rules. The only difference is that our base unit is talking about volume liters, right? So we're starting with milliliter. which is all the way over here at the milk unit. We want to get to liters. Liter is just the base unit, right? There's no prefix in front of it, so that gets us to this spot here. So I have to take my decimal and move it 1, 2, 3 hops to the left. Where is my decimal in this number here? It's living at the end. So I move the decimal 3 hops to the left, 1, 2, 3, and we get 30.5 liters. Why don't I include these zeros in it? Because I don't know if they're significant or not. All right, we talked about sig figs last time. I know the 3 is significant, I know the 5 is significant, and I know that 0 is significant. These zeros, it's sort of written in an ambiguous way, so I can't tell, so I would just not include them. Right? Isn't that kind of nifty to move through units in that way? It's a lot faster than unit conversion dimensional analysis, which is what we have to do within the British system, and I will definitely show you guys that. So let's head back over to the slides. As far as choosing a prefix, yeah, a lot of times you want to choose a prefix multiplier that makes sense for whatever the unit is. So like here they're saying, hey, a chemical bond is about 1.2 times 10 to the negative 10 meter. So they're using a base unit of meter, and it's a very small amount. It's like, you know, the decimal's got to get moved out 10 places in the direction that makes a smaller number. So this is sort of incomprehensible, like what that even means. So you may want to change the prefix to something like a pico or a nano. Preferably you go with whatever the smaller unit is. So the pico is 10 to the negative 12th, the nano is 10 to the negative 9th. Either of these would be appropriate, but the pico usually would probably work better. When you convert it to a picometer, instead of having to say, hey, I've got 1.2 times 10 to the negative 10th meters, you can say, hey, I have 120 picometers. Now, a picometer might not make sense to you because you've not used the unit picometer a whole lot, but let's say you knew that the distance of, you know, let's say, I don't know, the width of a hydrogen atom is 50 picometers. Then you have something that you can kind of relate it to, because 120 is a number that we can comprehend. 1.2 times 10 to the negative 10th is sort of like junk information. So, you know, when we were looking at this one right here, this would probably be a more appropriate unit out of the two of these. If I said, hey, I need you to deliver a letter and I need you to travel 1,720,000 centimeters to do it. It's like, what does that even mean? Is that across my house or is that to the moon? Well, it's neither of those. It's somewhere in between, right? It's about 17.2 kilometers. This is sort of meaningless in the centimeter unit. When we get into the kilometer unit, the kilometer is just over half a mile. That's, I probably wouldn't want to walk there. I'd probably want to drive there, right? But this, I can't really tell. So that's why, you know, sometimes shifting out the prefix in the unit is useful. So there are some units that are what we call derived units, and a derived unit is a unit that's made up of other units. Volume is a good example of a derived unit. Now we can use the unit for there's a bunch of different units we can use for volume. One of them is a liter. This in itself isn't a derived unit. I can't get it down to simpler units. But other things we can use for volume are things like meter cubed or centimeter cubed. Have you heard of a cc, like administer 50 cc's? That's a centimeter cubed. We also have a millimeter cubed. You may have heard of something called a cubic yard if you've ever done any landscaping or gotten mulch delivered to your house, a cubic yard. Why these things here are derived units, and that you have to take another unit and multiply it by some type of unit. So area is a derived unit, it's length times width. Volume is a derived unit, it's length times width times height. So we're taking a simplified unit and combining it. One nifty relationship is that a cc is the same thing as a centimeter cubed, and that is also the same thing as a milliliter. Okay, so easy way to convert back and forth between these. And we'll do a bunch of practice with those throughout the semester. So if I gave you something like this, given that we have 1.3 miles, and I want to find how many inches this is. There's no nifty way like the metric system to just move the decimal around, okay? In this case, we have to set the problem up using dimensional analysis and unit conversions, which sounds, I think, scarier than it actually is. And this is something you want to learn, because I do feel like general chem or intro chemistry is just unit conversions. Most of what we do the whole semester is this sort of process over and over again. So there are two ways that we can sort of approach our problems. One is a unit conversion type. That is where I feel like most of what we spend our class in. And that will be where we use an equivalency or two things that are equal to each other. We try and drop out unities or units to convert from one unit to another. Another way that we can solve problems is with a specific equation. So this problem up here is a unit conversion problem. I'm trying to go from miles into inches. I'm changing from one unit to another. A specific equation would be something like density equals mass over volume, okay? You've got an equation. I would give you like 2 of the 3 variables, and you would isolate and solve for the third. Really, those two things cover like 95% of the math problems that we do in this class. Let's talk about that first one, unit conversions. So we use this thing called dimensional analysis, which is just a fancy way of saying that we're going to multiply, divide, and cancel out algebraic quantities using conversion factors. Always, this is just good, proper mathing. Always write your number with its associated unit, okay? So don't ever just write like 3.47. 3.47 what? So make sure if you're talking about 3.47 grams, you give it a unit of gram. If you're talking about 3.47 centimeters, you add that. I mean, these two things are describing two different measurements. Always include units in your calculations, dividing and multiplying them as if they were algebraic quantities. So things above and below get canceled. Do not let units just appear or disappear. Yeah, okay, let's practice it out. This is money right here, okay? So this is the sort of basic structure of all unit conversions or dimensional analysis. You start always with your information given. You're going to multiply it by some sort of conversion factor, and you're going to receive the information sought. Or if we expand that out, we're going to start with our given unit. We're going to multiply it by our conversion factor, and our conversion factor will be the desired unit over the given unit. The given unit over here is above an inferred fraction bar, right? So there's sort of an inferred line with a 1 underneath it. They just don't write that in. That given unit is going to cancel with the given unit below the fraction bar here, and you'll be left with just a desired unit. So let's do like a real simple one that you probably wouldn't even need to set up in this. And you're like, why am I going to set it up like this? Because when the problems aren't quite as intuitive, you're going to want to have a system to follow. So I'll write this on the other slide as well. So we said we take our given unit, we're going to multiply it by a conversion factor that has the desired unit on top and the given unit on the bottom. And what will happen is these things will cross out and we'll be left with a number that has just the desired unit. So we've converted or we've changed the starting unit to the desired ending unit. Now, what is this thing here? This is known as a conversion factor. How many conversion factors are there in the world? Oh, so many. What are some examples of a conversion factor? 1 inch, no, let's go with 12 inches, is equal to or equivalent to 1 foot. This form, the way that it's written here, is called an equality. So it's two different units that are equal to each other, right? 12 inches is always equal to 1 foot. Another way that we can write this, which is more useful for this, is to put one above and below the other one in a conversion factor. So 12 inches is equivalent to 1 foot, or we could write it like this: 1 foot on the top over 12 inches. Why can we write this thing like this? Because anything over itself, two things that are equal each other over themselves, is equal to 1, right? 3 divided by 3 is 1. 1.5 divided by 1.5 is 1. And we're assuming these are equal to each other. So this conversion factor is just a value of 1. Another conversion factor, 1 meter is equivalent to 100 centimeters. So I can write that like this as an equality, or which tends to be more useful for our dimensional analysis, is to say, hey, 1 meter over 100 centimeters, or we could put 100 centimeters on top and 1 meter on the bottom. Now, which one we use is dependent on which unit we want to get rid of, right? And I'll show you guys that later. So we can use either, A or B, depending on which direction. Are we going from inches to feet, or are we going from feet to inches? I'm going to write 2 more equalities, and I want you to tell me the 2 different types of conversion factors that you can derive from it. So 1 kilogram is equivalent to 2.2 pounds. And then also 1 mile is equivalent to 5,280 feet. All right, so write 2 different conversion factors. I'm gonna give you a minute. All right, so it shouldn't be too difficult. In this first one here, I could write 1 kilogram on the top and the 2.2 pounds on the bottom, or I could write the 2.2 pounds on the top and the 1 kilogram on the bottom. Either way, those are appropriate conversion factors. Now, which one you use, again, is dependent on the problem. Things you don't want to write. So I'm going to write this in red. I don't want you to write this down as something you would use. These are bad. Very bad. Would be 2.2 kilograms is equivalent to 1 pound. Okay, why does that not work? Well, what's happened is we've taken the number and we've mixed it up with the incorrect unit. So don't do that. That no longer preserves the correct relationship. Or if we were to write like, 1 pound, 1 pound over 2.2 kilograms. We don't like that. The 2.2 really needs to stick with the pound, and the 1 needs to stick with the kilogram. So we don't like those. So we don't like them so much, I'm going to erase them. But I think it's good sometimes to show what common mistakes I see. This one here, and again, you always want to pair the unit and the number correctly. So 1 mile can go on top, 5,280 feet go on the bottom, or we could put the 5,280 feet on top for every 1 mile. What is not going to work out for us is 1 foot is equivalent to 5,280 miles. Okay, there's definitely no way you can step from New York to San Francisco, which is probably close to that distance in 1 foot. So you all feel okay with with what a conversion factor is. You're going to want to have some of these available to you. Let's go over to Moodle real quick. If we were in a traditional setting, I would expect you guys to have some of the conversions memorized. But I do help out students a little bit. Since we're online, you can add notes to this, and that's fine. But if you want to go here, periodic table and formula sheet, these are two things you probably want to print out next time you get access to a printer. So the periodic chart we'll get into next time, but this formula sheet, this is the standard formula sheet we use really for all of our intro chem classes. And what you'll see up at the top are a bunch of common conversion factors. There's that one we talked about, 2.2 pounds is equal to 1 kilogram, right? And there's some other ones in there. Are there more conversion factors than this? Oh yeah, there's so many conversion factors. So you may want to write some other ones that you use commonly, but I would say like when you're going to run your test, have this next to you just to help you out. So how do we use these conversion factors? We've got that sort of obscure equation thingy. This thing here, right? So we've got given unit, desired unit, over given unit equals our desired unit. So I'm going to get rid of these guys down here. And let's just work with the inch feet one. Looks like I got something in the chat. Let's check that out real quick. Oh yeah, thank you, Joanne. Yeah, the formula sheet is also in the lab packet as well, if you don't want to print it out. Thank you for that. Yeah, I forgot about that. It's you've got a physical copy in there. All right, so anytime we're given a word problem, which is quite often in chemistry, we want to organize the information. I think people get really freaked out by word problems because it gets all jumbled and what am I supposed to do and where am I supposed to go? And so you are going to want to practice what the slides call critical thinking skills. Critical thinking skills is not something that I can give to you, but it's something like a muscle that we can train. The more practice problems you do, the better your critical thinking skills are going to be, right? You do a bunch of these conversion factors at some point, it doesn't really matter what I throw at you, you're going to understand how to do it. Okay, so the best way to get good at this is practice, 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 practice. But we'll do something real simple here. So how many inches are in 4 feet? Okay. So quite a few of you are probably looking at this problem saying, how many inches are in 4 feet? Okay, yeah, I need to take 4 times 12, right? And then I figure out how many inches are in there. I want us to set this up in dimensional analysis. So the first thing that we like to do is organize our information, and you'll see me do this repeatedly. So I'm going to write what my given information is. And in this case, my given information is the number that I have. I don't want to just write 4. I want to write 4 feet. I always want to include my unit, especially if I'm doing a unit conversion. I need to know where I'm starting. Then I'm going to write what I'm trying to find. Okay, in this problem, it says how many inches. So I'm trying to find inches. If I was trying to find centimeters, I'd work on that, but I'm trying to go from feet to inches. So the slides are going to kind of guide you into creating what is known as a flow chart. So it's kind of like this, but they add a little bit more. So we're going to put feet, they put it in a nifty box, they put inches in a nifty box, and then they put an arrow between it. The arrow here is representing how I get from here to here. So if I'm trying to change units, this is where I want to do dimensional analysis, and I need one of these conversion factors. Well, you'll notice that the conversion factor we need is this guy right here. So it might help you to write, that my conversion factor, you can write it underneath here, is 12 inches is equivalent to 1 foot. If you like this flowchart area thing here, you can write it right underneath the arrow. You can say, hey, 12 inches is equivalent to 1 foot. So to set this problem up, I want to start it, or I want to set it up just like this. So I start with the given unit. So that's feet, or not just given unit, but the given piece of information. So even if you want to write above this given info. So my given info is 4 feet. I'm going to write 4 feet. You can, if you want, you can put a line with a 1 underneath it, or you can just assume that there's a 1 underneath it. Any number that you write has some sort of inferred 1 underneath it. I'm not going to put that in. So I'm going to put a multiple symbol or multiply symbol, and then I'm going to write my conversion factor. So here it is as an equality. These two are much more useful. Now, which direction am I going from? Well, I want to go from feet into inches. So the unit that I'm starting with always has to go on the bottom. So if feet is on top here, I want feet to go on the bottom here. And then inches is going to go on top. Now I need to fill the numbers in. So we're using this first guy here. 12 inches for every 1 foot. What will happen to the unit for feet is that feet will disappear, cancel out, and we'll be left with a number that just has the unit of inches. So yes, at the end of the day, we did take 4 and just multiply it by 12. But when we don't have something that's so intuitive with the conversion factor, I just wanted you to see how the structure was. So we've got 12, and we're going to multiply it, or rather we're going to take 4 and we're going to multiply it by 12. Anything that's above the fraction bar are going to be multipliers. Anything that's below fraction bars are going to be dividers. So in this case, we're taking 4 times 12, and then we're dividing it by 1. We don't really need to divide it by 1. And we get 48 inches. Okay, so there's 48 inches in every 4 feet. Seems like a lot of work for what maybe is a simple problem. Let's do another one using just these conversion factors. And then we'll try something that isn't so familiar. All right, so I'm gonna have you guys solve this one. How many feet are in 1,350 inches? So I want you to try and set it up just like I had set that last problem up. Tell me what the given is, tell me what you're trying to find, tell me which conversion factor you like, and then set it up in the dimensional analysis. And we'll meet back in a minute or 2. Samantha said, in the last problem, wouldn't you have to take into account the lowest sig fig, which is 1. Remembered conversion factors have an infinite number of significant figures. We're going to assume that that is the most precise 12 and the most precise one that have ever existed, right? Is a perfect definition. So in general, the number of sig figs in your given information will be pretty much what limits your dimensional analysis. Give you guys just another 20 seconds to finish this one up. So yes, with that, round to the correct number of significant figures, because I still care about sig figs right now. All right, so this problem, little different than the last one in that we're going in the opposite direction as far as what unit we're starting with and what we're trying to find. We're starting with an inch value, right? So 1,350 inches. And I want to find how many feet this is. So the conversion factor, we're still using the same conversion factor, but I'm actually going to use this thing here because I want inches to go away. So I start with my given, always 1,350 inches. And then I'm going to multiply it by my conversion factor. So look at what's here. Whatever the unit is here, it needs to be the thing on the bottom, okay? Crisscross. The other unit goes on the top, so feet go on the top, and then just make sure you fill the right numbers in. So don't say 1 inch equals 12 feet. 1 foot equals 12 inches. So we end up taking our number and dividing it by 12. So 1,350, and we divide it by 12. We get 2.5. The unit on this is feet. I need to round to 3 significant figures. If we look at this number here, I know the 1 is significant. I know the 3 and the 5 are significant. Is the 0 significant? I don't know. I can't tell. So I need to round to 3 sig figs. Can only honor the least precise. So I'm going to round this to 113 feet. That would be our final answer. Mastering Chemistry likes for you to round to correct sig figs. Any questions on what the whole thing means now? Can you see how this and this fit together? And I know it seems like a lot more work than maybe you want to perform, but this is going to be really helpful. Let's try another one. So I'm going to clear all this. So we had said something about 1 kilogram is equivalent to 2.2 pounds. So how many kilograms are in 1.37 times 10 to the 6 pounds? I'm going to give you a little scientific notation so you can work on getting that into your calculator. So set this up in dimensional analysis. Again, write your given, what you're trying to find, what your conversion factor is. Hint, hint, wink, wink, it's up here. And then plug it in. Round to the correct sig figs too. I'll give you guys 2 minutes. All right, so our given information here, we've got 1.37 times 10 to the 6 pounds. I wouldn't recommend like moving the decimal out and writing this in an expanded form. I would just plug it into your calculator like this. We're trying to find. All right. Trying to find kilograms. So when plugging this in, start with your given information. Well, you need your conversion factor. It's this thing up here. So I have 1.37 times 10 to the 6, and this is pounds. I need to multiply this by some sort of conversion factor, and the conversion factor here, well, if pounds are my given, I need to put pounds on the bottom. Kilogram will need to go on top. Then we just need to pair the numbers up appropriately. So 1 kilogram is always equal to 2.2 pounds. If you had this flip-flopped, make note of that you want these things to be opposite each other. When I plug this into my calculator, you can write it as 1.37 times 10 to the caret 6, or you can write it in your calculator as 1.37, and then there's an EE button to the 6. That's usually what I use. So here, I'll show you here on my cell phone. You turn your cell phone over, you get more of a scientific calculator. There's going to be an EE button right there, okay, next to the 1. You don't want to write 1.37 times 10 to the EE6. You either use times 10 to the, or you use the EE button. This is this whole functionality right here. Just know that those are the same. So I take my 1.37 EE to the 6th power. And then I'm going to divide it by 2.2. Why do I divide? Because it's below the fraction bar, right? I get a long number, 6222727, and then a bunch of decimals, 273, whatever, lots of numbers. How many sig figs? Go with your given information. So we get 3 sig figs, 1, 2, 3. So I'm going to keep the 6, I'm going to keep the 2, and I'm going to keep the 2. The 7 tells this 2 to round up, so it becomes 6, 2, 3, and then I fill those slots in with zeros. Okay, and then give it a unit of kilogram. Don't forget to put your unit at the end. That's the whole point of dimensional analysis, is to shift the unit. Questions? Let's do one within the metric system, just so you can see how we can either use King Henry died before drinking chocolate milk, or we can use this process of dimensional analysis. So how many, I don't know, how many millimeters are in 4.6 meters? So A and B, 2 ways to solve this one. I'm given a unit of meter and I'm trying to solve for millimeter. So this is within the metric system, which means that I can use King Henry died before drinking chocolate milk. So King Henry died before drinking chocolate milk. My unit is starting at the base. I'm trying to get to millimeter. So that would require me to go 1, 2, 3 hops to the right. So my 4.6, 1, 2, 3 hops, fill it in. It becomes 4,600 millimeters. Pretty fast, nifty. The other way to do it is to run this in dimensional analysis, which is where we use a conversion factor. I'm given that I have 4.6 meters. I'm trying to find the millimeters. Okay, so I need a relationship. Well, 1 meter is equivalent to 1,000 millimeters. That is the definition of a millimeter and a meter. I set it up, start with my given 4.6 meters times my relationship here. I want to put the meter on the bottom and I want to put the 1,000 millimeters on the top. What happens to the meters? They cancel and I'll be left with the unit of millimeters. Hey, surprise, surprise, you get the same answer. It's just two different ways to solve it. This way for me is much faster. So you'll see me hop a lot back and forth. Just because I'd rather, move the decimal 3 places than have to like write all this out and remember the conversion factor specifically for that. It's up to you. You can solve it either way, A or B for those. Any questions on this here, on either one of these setups? So everything we've done thus far with conversion factors have been single step, very simple. What if it becomes a little bit more complicated? So let's say I go, how many centimeters are in 8.42 feet? So my given piece of information is 8.42 feet. What I'm trying to find are centimeters. Now, is there a conversion factor between feet and centimeters? I mean, there probably is. I just don't know it. Okay, but I do know how many inches are in a feet, and I do know how many inches in centimeters are equivalent to each other. If we go back here to our formula sheet, there's inch to centimeter, and then you already know inch to feet. So this is going to be like kind of like a game of leapfrog, where we're going to jump through sort of a middle unit and before we get to the end. So I'm going to draw one of those flow charts that the text likes to kind of guide us through. So I'm going to start with feet. And because I don't have an easy way to get from feet to centimeter, I'm going to go feet first into inches. All right, I'm going to take my feet and I'm first going to convert it to inches. And then after I get into inches, I'm going to get it into centimeters. Okay, so it's a two-step problem. What's the relationship between feet and inches? We already know this, right? 1 foot is equivalent to 10 inches. Where am I? 12 inches. 1 foot is equivalent to 12 inches. And then what's the relationship between inches and centimeters? This is probably a new unit conversion for you, but it's on that formula sheet and you're going to see it quite often, okay? 1 inch is equivalent to 2.54 centimeters. You can trust me on that. So when solving this problem, I'm going to first just try and get from box 1 to box 2. I'm going to ignore the whole centimeter thing for right now. My goal is just to get from feet to inches. So I'm going to start with the 8.4 feet, 8.42 feet rather. And my goal right now is just to get it into inches. All right, so I'm going to put feet on the bottom and I'm going to put inches on the top. 1 foot for every 12 inches. Some people like to stop and solve for it here and then continue on. I will always chain mine together. So if you notice, feet cancel out. There's a foot above and there's a foot below. It goes away. That has gotten me to the second box. So now I want to go from the second box to the third box. So we don't care about feet anymore. Feet have disappeared. We're in inches. Inch is on top, but do I want to end up with inch? No. So inch needs to go in this second conversion, inch needs to go on the bottom. When inch goes on the bottom, centimeter goes on the top. Let's add our unit, 1 inch for every 2.54 centimeters. Look at that, inch disappears. It's like it never happened. And then you'll just be left with the unit of centimeter. I'll round whatever the number is to 3 sig figs, 8.42 times 12 times 2.54. 4. I get 256, 257 centimeters. The feet, 1 away, the inches, 1 away. Okay. Remember, you multiply anything on the top, you divide by anything on the bottom. I didn't plug in the ones because they don't have any effect. So 2-step problem. You could have 3-step problems. You could have 4-step problems. This is where that critical thinking comes in of like, how do I formulate this? So I have feet, I want centimeters, realizing that there's that mid step. I'm going to have you guys use the same sort of conversion factors, but let's try it a different way. So how many feet are in 7,200 inches? No, centimeters. I want you to do a little more work than that. Centimeters. Okay, so how many feet are in 7,200 centimeters? I'll give you guys about 2-3 minutes to mess around with it. Make sure you're using the right conversion factors. Make a flow chart if you need to. Figure out how you're going to hop around, and then we'll meet back. inches, I'm going to put you on top. All right, that means 1 inch, 2.54 centimeters. So we're dividing by that. The next step is to get us from inches into feet. Inches goes on the bottom, feet goes on the top. 12 inches for every 1. You guys see how these have gotten flipped over? The reason they're flipped is because we're going in the other direction. Oh. These would probably help, wouldn't they? Just talking to myself. It's okay. No worries. All right. So I can't hear you there. Oh my gosh. It's been a long day. My kids have been out of school for too long because of the snow and everything. They need to go back. And they're not going back for the rest of the week. Ah, are you guys having the same thing? Oh, come on, Henderson County, step it up. All right. So let me say what I was saying again. So we start with centimeters and we're trying to go towards feet. So our flow chart is going to be flipped, right? We're going in the opposite direction, which means as far as our conversion factors are concerned, they're flip-flopped, right? Centimeter is on the bottom, foot is on the bottom because of the direction that we're going in. I don't really think about it as like, oh, if I'm going from feet to centimeters, I need to make sure that this is on top and this. I just look at what does it tell me to do? If centimeter is here, centimeter needs to be down here. If inch is here, inch needs to be down here. And I just need to continue the process of canceling. So here we've got a divide. So we take our 7,200. We're going to divide by 2.54. The way that I plug this into my calculator is I take the 7,200, I divide it by 2.54 and I equal it out. And then I divide by 12. If you would prefer to take 2.54 and multiply it by 12 and then divide the number by that, you can do it that way as well. I just find it's really fast for me to take the number and divide it multiple times. So the only unit left is feet, which is what we were asking for. 236. But I only get 2 sig figs. So 240 feet. Okay, the 6 tells the 3 to round up. Again, rounding super important in this first chapter. As these problems get more complicated later on in the semester, there's a little more wiggle room if you wrote 236 versus 240. I wouldn't stress too much about it. I'm going to have you do one more dimensional analysis. That's a multi-hop problem because I want you to practice your skills. So how many seconds are in 28 days? And you may be like really skilled at math and know how many seconds are in a day, but probably not. So this is a multi-step hop from days to the next unit to the next unit to the next unit. All right, I'll give you guys 2 minutes to mess around with that. Okay, so we're given that we have 28 days. And we're trying to find seconds. Every now and then I'll get a student that's like, well, I know what the relationship is. One day has this many seconds in it. And that's awesome. If you know that, use it. I don't have that off the top of my head, but I do know days in relationship to hours. And then I know hours into minutes. And then I know minutes into seconds, right? Those I know off the top of my head. 24 hours in a day, 60 minutes in an hour, 60 seconds in a minute. So I'm going to use those as my conversion factors. So we've got 1, 2, 3 hops for this one. So we'll start with 28 days. 1 day, 24 hours. 1 hour. So the day cancels the hour. I want that to go on the bottom. Will give me 60 minutes. That gets me to this place here. And then the last step is to go from minutes to seconds, right? And we know that 1 minute has 60 seconds. So the minutes will cancel. And so we'll just be left with a value of seconds. Let me just double check that I got that right. So, all right, so we get a large number, which makes sense. 2,419,200, 2 sig figs. So I'm going to round it to 2.4 times 10 to the 6th. I wrote it in scientific notation, seconds. If you're like, that's not what I had, that's not what I had. Okay, I'll write it a different way. 400,000 seconds. Those are saying the same thing, right? This is just written in a scientific notation form. You guys seen how this system works over and over? Hopefully that kind of strange generic equation prior makes a little bit more sense. Like when we look at, go back to our slides, this thing here, right? So now it's like you see, okay, I'm going to start with my given unit. I'm going to use my conversion factor, make sure those are opposites so they can cancel, and I should end up with my desired unit. You can chain a bunch of them together. Okay, what is a solution map? This is those boxes that I was talking about. They like to figure out what are you starting, what are you ending, write your conversion factor as your arrow. Write your given, write what you're trying to find, write a solution map if need be, and then write the correct conversion factors. General problem solving strategy. This is all part of, being a good problem solver. Sort your information, strategize, that's the critical thinking, solve the problem, and then check your answer. What students sometimes do is they try and jump right to this. Like get a word problem, like, oh, I'm going to solve it. Well, before you're going to solve the problem, sort the information out. Then figure out a path to get you from your start to your end. And then always, guys, check. I mean, if you have the time to, check your answers. So here was a multi-step problem. We've already worked with centimeters to feet. But right, if you want to go from centimeters to feet, you've got to take that leapfrog in the center at inches. Round to correct sig figs. Sometimes we don't do this a whole lot. Like I'm not really going to test you on it, but let's say we had something like in miles and gallon. So we had a double unit, 48.0 miles to the gallon. That's a double unit where we have miles on the top and gallon on the bottom. If I wanted to convert this to, let's say, kilometers per liter, because you're going over to Europe or something, you're bringing your car over to Europe, and we want this mile to become a kilometer and we want this gallon to become a liter. Well, you go through the same process. You can start with one of the units. So in this case, I want to get mile into kilometer. So kilometer goes on top, mile goes on the bottom. This is the relationship. Just trust that that's the conversion factor. And what you'll see is that the mile cancels. You also, though, have to do the same thing with gallon. Now, do you see how gallon in the initial unit is on the bottom? Okay, it's a distance per volume. We want to keep the volume unit on the bottom. So if gallon is below here, we need to actually put gallon above here because that allows it to cancel out. And then what are you left with? You're left with liter. So it becomes kilometer on the top and liter on the bottom, and we want both of those units. We want a double unit, right? So if you ever have something like that and you've got a unit on the bottom, make sure you put its cancellation on the top. But again, I don't test you guys on that. You may see a problem on mastering chemistry with it. You will not see anything come up on an exam where you have like a double unit like that. That's kind of why I'm breezing over it. Convert units raised to a power where we don't, no, we're not going to spend a whole lot of time on that. Okay, so I said there were two different ways that we did, most of the math problems. And the first one was the dimensional analysis conversion factors. The second one is plug and chug equations. This one you probably will feel a little bit more comfortable with, where you have a known equation and you stick numbers in to solve for the one you don't know. So let's talk about density. Density is a physical property, meaning it's inherent to whatever the material is. So if you're iron, you'll have a certain density. If you're gold, you'll have a certain density, so on and so on. So let's say, why do some people spend more than $3,000 for a bicycle made out of titanium? And a lot of times students will say, because it's lighter. Okay, well, it is lighter, but I could give you a lighter bicycle that's like as big as my hand, right? And that's not going to be a very useful bicycle for you. So we want to keep the same volume so that it fits your body, and we want it to have a lower mass, which means we want it to be less dense. All right, so when we talk about these more expensive bikes, we're not talking about the bike, quote unquote, being lighter, but we're actually talking about it having a lower density. A traditional iron bicycle, like old frame or steel frame, has a density of about 7.86 grams per centimeter cubed. So 7.86 grams fit into a centimeter cubed versus a titanium bike, which is 4.50 grams per centimeter cubed, less mass in the same volume. You can see that this is a derived unit. Density is a derived unit, meaning it's a double unit. Density will always have two units, one over the other. The top one for density will be its mass. So density is always going to equal mass over volume. So its unit will have to have a mass value on top and a volume unit on the bottom. Common units we see for density: gram per centimeter cubed, gram per milliliter, pound per yard cubed. There's all sorts of different things. Top one has to be talking about its mass / weight. Bottom one has to be talking about some unit of volume or space. So when looking at this equation, we have 1, 2, 3 variables. Go back in time, back to, what was it, algebra. When you have equation with 3 variables, you will be given 2 and you solve for the third, right? If I gave you just one of these, you could not solve for the other 2, okay? So you'll be given 2 and you'll solve for the third. Sometimes you'll be given mass and volume and you solve for density. That's great. Sometimes you're given like density and volume and you have to solve for mass. So you need to be able to isolate a variable, which means move these things around so that you get it isolated for this specific thing you're solving for. So let's isolate variables here for a minute. All right, density equals mass over volume. So if the problem gave you mass and volume and you were solving for density, you don't have to do anything to the equation. It is perfect the way it is. But let's say you're given density and volume, and I want you to solve for mass. Okay, so my initial equation is density equals mass over volume. If I want to get mass by itself, I need to get rid of the other stuff that's on this side. What is on this side with the mass? It's this volume thing. Well, what is our volume doing? It's sitting below a fraction bar, meaning it's acting as a divisor. So in order to get rid of it, I need to multiply by volume. That means that there'll be a volume on the top and a volume on the bottom. Now, whatever I do on one side, I have to do on the other. That's how we move it to the other side. So I multiply this by volume, right? There, our volume disappears on the right side and it's on the left side. Now our new equation tells us, hey, volume times density equals mass. We've now isolated for mass. I think the most difficult is solving for volume underneath the fraction bar. So if I want to solve for volume, I'll use different color here. Density equals mass over volume. All right, I want to solve for volume. So I want to get volume by itself. So what I see happen a lot is students will go, okay, well, I'll get rid of mass. So I'm going to divide this side by mass and I'm going to divide this side by mass. That's great. Masses cancel. But look at where volume is. It's below the fraction bar. So this is not, and then a lot of times students will write, okay, so volume equals density divided by mass. No, 1 over volume equals density divided by mass. So I then need to flip these and flip these, or volume will actually equal mass over density. Okay, another way to do that, density equals mass over volume. If you're trying to get volume, just get it out from underneath the fraction bar. So multiply by volume and multiply by volume. That will disappear. We now have volume times density equals mass. And then let's move density over. So divide by D and divide by D cancels. And what do we get? Volume equals mass divided by density. All right, that's another way to do it. What I don't want you to do is what was happening at that very first step, which is, we'll write it in red, density equals mass over volume. And you right off the bat go divide by mass, bye-bye, divide by mass, bye-bye, and then say volume equals density over mass. This is the inverse, 1 over volume. Okay. So you will have to isolate variables. I think the most really that you're going to see in an equation is maybe 4 variables. If you have a lot of trouble with isolating variables, I'd recommend getting into the tutoring lab, and they can just kind of break down isolating variables more, or you can always check in with me during office hours and we can go over some more stuff with isolating variables. So with density, the density equals mass over volume. Great. Let's say we've got a problem here that says calculating density. We're not going to use dimensional analysis for this. We're going to use plug and check. So a sample of a liquid has a volume of 22.5 milliliters and a mass of 27.2 grams. Find its density. So we know density equals mass over volume. It's giving us the mass and the volume. It won't always say the volume is this and the mass is this. Sometimes it'll just say, hey, a liquid has takes up 22.5 milliliters and is 27.2 grams. And you have to get in the habit of seeing that word G, gram, and know that it's talking about mass, right? And that when you see something like milliliter or centimeter cube, that is referring to volume. So we've got our given information here, which is that we have 27.2 grams. We also have 22.5 milliliters. This here is my mass. This here is my volume. I still would sort and organize your information. Write out your equation, density equals mass over volume, and then you plug it in, right? So we plug our M value in on top and we plug our V value in on bottom. We divide them out, we get 1.21. They rounded to 3 sig figs because 3 sig figs. And look at what they did with the units. They kept both of them because gram and milliliter will not cancel each other out. So they both follow over. And we like that because density is a mass per volume unit. So we want to keep both of those. The problem doesn't explicitly say, hey, I want it in kilograms per yard cube. So if it doesn't explicitly say, just do whatever the units are that they give you. Don't make it more work than you have to. So let me give you a density problem here. What is the density of a metal? Let's of 33.7 grams of a metal that occupies 4.81 centimeters cubed. You guys have 2 minutes. Okay, so what is the density of these two things that are properties of this mysterious metal? So we're given 33.7 grams. Gram is a mass value, so that's my M. 4.81 centimeters cubed. Doesn't explicitly say it's a volume, but that's talking about volume. Okay, a cubed length times width times height. So what are we trying to find? We're trying to find density. Density will equal mass over volume. So now we can just stick it in. Density is going to equal that 33.7 grams divided by 4.81 centimeters cubed. I take those two, I divide it out. The problem doesn't say, hey, convert it to anything outside of this. So we're just going to keep it in those units, 33.7 divided by the 4.81. And we get, we need 3 sig figs, 7.01. And the unit on this is gram per centimeter cubed. So let's look at a problem if we are given density and another thing, and we're trying to solve for the remainder unit. So I want you to work on this problem here. It says, for a liquid substance with a density of 1.32 grams per centimeter cubed, what volume should be measured to deliver a mass of 68.4 grams? So in this problem, we know the density and we know the mass. You need to solve for volume. So go ahead and isolate for the volume variable, or if you like, you can plug and chug and then isolate. Some people like to do it that way. And we will come back in 2 minutes. Okay, so in this problem, we are not trying to solve for density. We're actually trying to solve for volume. So our given information, we have 1.32 grams per centimeter cubed. And we also, that's the density. And we also know that we have 68.4 grams, which is the mass. And I want to find the volume. So equation originally is density equals mass over volume. When I isolate for volume, and again, some people like to just plug the numbers in and then isolate from there. That's fine if you want to do it that way. Volume is going to equal mass divided by, yes, volume is going to equal mass divided by density. So we'll plug our mass in for our numerator. The volume is going to equal 68.4, and I always include my units when I'm plugging and chugging because the units will cancel out, or at least the ones that I don't want to have around, hopefully, divided by this 1.32 grams per centimeter cubed. And what you'll see is grams cancel, and then centimeter is below a fraction bar and then below another fraction bar. So it's like divided and divided, which actually throws it back up on top. So we get a unit of centimeter cubed, which is a volume unit. That's great. We like that when we're solving for volume. We're just going to take that 68.4 and divide it by 1.32, 52. Looks like we get 52 centimeters. No, 366. Okay, let me give it a little more significance. 51.8. 51.8 centimeters cubed. And I believe the slides went through that. Yeah. Oh, I guess this problem doesn't explicitly say that it wants it in milliliters. So they went through another step of converting it to milliliters, but know that centimeter cubed, this is a handy thing, centimeter cubed and milliliter are the same thing. It's a 1-to-1 ratio. So if you know that you had 51.8 centimeters cubed, you also have 51.8 milliliters. So that's kind of a handy thing to have in your back pocket or have on your formula sheet if it's not already on there. I'm going to give you guys one of these where you solve for something outside of density. So what mass of a liquid with density of 3.87 grams per centimeter cube takes up 145 centimeters cubed. All right, so we're trying to figure out mass. So what is our mass? Our density is 3.87 grams per centimeter cubed. And our volume doesn't say volume, but it says takes up a certain amount of space. And again, this is a volume unit, 145 centimeters cubed. Okay, so if density equals mass over volume, and I want to get volume, rather mass by itself, I'm going to move volume to the other side. So mass should equal density times volume. Plug in from there. So density is 3.87, and again, I put the units in, grams per centimeter cubed. We're going to multiply that by 145 centimeters cubed. And look at that, centimeters will cancel. It's above the fraction bar here, it's below a fraction bar here, so it disappears. So we're just left with units of gram, which is a good unit to have for mass. Let me just double check my answer. All right, we'll go with 3 sig figs on this. 561 centimeters cubed. No. I saw everyone's face like, no. Okay, let me try 3.87 times 145. You guys aren't getting 561? Yeah.
I got 561.
561. Okay, yeah, okay. 561, yeah.
Grams and centimeters?
That's what it is. Yes. Thank
mass.
you. Thank you. Where am I? I'm done. Yeah, I think I'm going to call it after density here today. Yeah, so the unit is grams. Make sure you're using the right unit. Cool. So, just be aware if the information is given in different units, you've got to change it. Like, let's say that they gave you units of kilogram and the density was in gram per centimeter cube. Make sure you're converting kilogram to gram before you get it into the equation, because these variables need to match up with each other. One other thing I want to talk about, let's see, grams, yes, grams. Okay. That was all that was in the chat. Just a couple concept things about density. Here's a chart of common substances and their densities. You do want to know water's density, okay? It's a 1, easy to remember, 1 gram per centimeter cubed. So everything's based off of that. So water occupies 1 gram in a centimeter cubed. Ice is slightly less dense. Water is one of the few substances where its solid form is less dense than its liquid form. That is very cool. That is very important as well for the ecology of life and a lot of functions that happen on Earth. But because ice is less dense, it floats in water, right? So all these things would float in water. Ethanol, charcoal, oak, these things all float in water. Anything that's more dense will sink. Right? Have you guys ever made one of those gravity columns where you have a bunch of like materials in your house? Usually you use like soap, you use some sort of oil, water, and you can dye them different colors and mix them together, and you'll get this these different layers, and they'll stack in this specific order. So let's say we had some objects like we had charcoal, ethanol, ice, water, and glass. Right, they would fall into this order. So the oak would be on top, then it would be the ethanol, then the ice, then the water, then the glass at the bottom. We'd get these different layerings. Let's see, I think that is it for this chapter. Yeah, so that's the end of chapter 2. So it's all that initial stuff, just talking about, scientific notation, significant figures. And we went over metric unit, we went over conversion factors, and we went over density plugging and chugging. We're going to do some more plug and chug in chapter 3, but I think we're going to stop there today because I can feel that my brain is starting to pour out of my ears. And that's not efficient or are good for anyone. So we will work on chapter 3 next week. We should be able to get through all of that. Make sure that you start looking at the labs and how that's going to kind of get situated. Definitely get your mastering chemistry done. If you have any questions, feel free to stay around. Otherwise, enjoy your weekend. I think we're supposed to get more snow again. Ugh. But hopefully they don't cancel school. So I will see you guys next week. Have a lovely weekend. Bye. Thanks, Lexi. Yeah, Megan, I hope we don't get any more snow. They need to take my kids.
Same here. I love my kids, but I'm ready for them to
Yeah,
come back to school.
Yeah, I know. I'm over you guys. I love you, but I'm over you.
Yeah, exactly. All right. Have a good weekend.
You too, Megan. Bye. Hey,
how you doing?
Good. How are you?
Good, thanks. I just thought I'd stick around because I emailed you about that question I had. Would you like to rather go over it via email, or do you want to do it now?
We can do it. We can do it now. It's always easier for me to explain stuff like Word,
totally
face to face, or Zoom to Zoom than it is over email.
Thank you so much. Yeah, that's awesome.
Okay,
cool.
So
yeah, it was just having I was having difficulty trying to really grasp the difference between law and theory, and just kind of when I would see an equation, if that ever includes as a theory, or if that should always be more considered law.
Yeah, so we're not going to spend a whole lot of time on this. I don't really test you guys on this stuff, but a theory is something that it's like widely accepted, but it's explaining something. So it's explaining why something is happening. Like the moon is rotating around the earth because of gravity, right? And when that's a theory, and when that theory has been accepted by the scientific community, it then shifts to become a law. Theories can be updated. Laws usually aren't updated. Laws tend to be things that like we observe and they're for sure. So the law of gravity, when I, lift my pencil up, it's going to drop, and it's going to drop at a specific velocity or increased velocity with acceleration. A theory could be like, gravity is the attraction between, the gluon force in quarks or something within an atom. We don't actually know why gravity acts the way it does, but it does act. It's going to continue to act in that way. But there's different theories, like there's string theory or there's quantum field theory, which are trying to explain things like gravity, which is a law.
Cool. So it's basically like I kind of just summarized it in this little map of concept for theory and then formula for law.
Yeah.
That kind of explains the theory.
Yeah. Yeah.
Okay, cool.
Yeah,
that really helps.
Cool.
Yeah.
Other questions from that chapter?
No, I think I'm good on that chapter. Thanks.
Okay, cool. How about chapter 2? How about all this stuff?
Just starting on chapter 2. So
okay.
Yeah.
Well, we lectured on it, so hopefully what we went over.
Oh yeah, it's looking good. Yeah,
okay, cool.
I'm liking the math, and it was really helpful how you described the multiplying the grams by the centimeters cubed, so that I remembered to multiply by the reciprocal, because I totally missed that. So that's super helpful.
That's very common. I see that
happen all right.
Quite a bit. Yeah.
Cool.
All right. Well, yeah, if you do have questions and stuff, I would say, unless it's like super urgent and you're like, I need you to tell me how to do this, I would like save them for a time that we can meet or Zoom and just say, hey, can we meet via Zoom for 5 minutes? Because it's gonna be way easier to explain it talking to you than it is through email.
Awesome.
That okay. Unless it's like,
thank you.
Unless it's like, hey, number 5 on the homework, I got this answer. Is this correct? That's different. But if it's like a explanation, yeah.
Okay, cool.
All right.
Thanks so much.
Yeah, have a good weekend.
You too. You too. I hope your kids get to go to school soon.
I know. All right.
All right. Bye.